I'm going to say, if the energy from here to here is lower for any given amount of charge, that will require that there's a potential difference from this end to this end. For that matter, it's that potential difference that ultimately drives the electric field, or describes electric field, that drives the movement of the charge in the first place. Okay, so in a very fundamental sense, there's all these little physical things that are going on that you typically don't want to worry about very much. So I'm going to call this here V1. There's some voltage difference between the two ends, and it's going to be lower because it's going to be describable in terms of the work required to move each charge across. Just like a ball having less potential energy when it gets dropped to the ground. Now, again, we have a connection here. And at all points along this wire, assumed wire connection, the electric potential is the same. Because all it is doing in functionality is connecting the outer end, or the exit end of this resistor to the entrance of this resistor. So all along here we have the same voltage. But if you follow the movement of electric charge, when it gets through this first resistor, it's then going to have to be pushed across or driven by the electric field inside the conductor through this second resistor. And there's work and there's energy transformation, which means that it's going to have less energy when it gets down here than it had when it was up here. Where does that energy go? Well, that's the heat that's generated as you push this thing through. So there's a corresponding voltage drop across that second resistor. But note, we say it's positive here and it's negative there, but this voltage is the same, if you will. This potential is the same here. The positive and the negative and the positive just represent the orientation relative to the resistor just previous and then succeeding this little connection. So I'm going to call, as the charge flows across the second element, I'm going to call that voltage V2. Now, no special laws of physics or special shortcuts required. When you get to this connection, when you get to the other side of that resistor, the only thing you have between that resistor and the connection to the power supply is a wire that does not effectively alter the electric potential. So what does that mean? It means that when you get back here, through whatever voltage rise, draw any interaction that's happening, by the time you get here, you get the same potential that you are over here, which happens to be 9 volts less than you are up here. Another way of saying it, if I started here and just walked my way around this electric circuit, this little loop connection, I started some voltage, I can call it 0, whatever, but whatever it is here, I go up 9 volts. I cross to the other side of the battery, go to the power supply. As I walk around, I get to the first resistor, there's a drop of that 9 volts. How much? I don't know, but I know that when I go across the second resistor, it also drops a little bit more. Once I'm here, I'm at the same point I am over here. So the only way that can be is if the voltage drop is the same as the voltage rise. Because I have to start and end at the same value if I go all the way around this loop. Okay? We don't have grandpa and metaphors or discussions of walking uphill barefoot both ways to school and back. Right? You start at a certain level, you go up, you come back down when you get to the same point. So that's fundamental, which tells us when you step around any loop process, all the rises and all the falls have to add up to 0. Because if they don't, you won't end up at the same electric potential than where you started. It's that simple. So as we step around this loop,
and it's a closed loop, and the key is that you have a way to go all the way around this sucker. Your starting or beginning voltage, I'm going to call it initial, has to be equal to your ending voltage. Let's call it V final, if you're going all the way around a closed loop. Well, the implication of that is that if you add everywhere that the potential difference changes in any way, whether it's rising or whether it's falling, this is what we know. It means that all the V increases will equal in magnitude to all of the voltage drops. The increases happen at power supplies. In order to have a potential difference increase, you have to have something that is adding energy, increasing the energy of the electric charge that's going from one side to the other, eh? You have to have something to do that. Nature doesn't add energy just for the hell of it. You have to have something artificial, something that's in process, that's generating that energy. Chemical reaction, electromagnetic generator, what have you. Hydroelectric, nuclear generator, doesn't matter. You have to have some sort of a generator or some sort of a power supply to add the energy at the expense of something else. So these increases occur due to power supplies. The voltage drops occur to whatever it is that adds load or requires work to push the charge through it. So in this particular case, we started here and we walked around this little loop clockwise. What we would say then is that the voltage associated with the power supply should be equal to the magnitude of the voltage drop across the first resistor, plus, in this case, the voltage drop across the second resistor. And this is always the case, and if you have other resistors or other elements, then you just, however many voltage drops you have across any loop, you'll have this basic relationship always. If you go all the way around it, yes, sir.
Is resistance the only factor that creates this requirement for work to drive the charge across, or is there anything else that we have?
No. Capacitors require work to charge.
Okay.
So there's a dynamic example. Inductors require work to drive current across because energy has to be overcome magnetic fields produced when charge immediately starts flowing around a coil. You generate a magnetic field, that magnetic field opposes the current that's generated, and you have, again, an energy requirement to push it across. And then you have solid-state devices that become much more complicated, but the same basic identity occurs. The only question is whether or not it's a static, can you calculate it as a single value, a single equation, or whether there's a time dependence to it. Or hypothetically, a temperature dependence or some other factor. But ultimately, it would relate to how, over time, everything transitions. But regardless, however these may be changing, for instance, slowly charging a capacitor, etc., they will always add up to this because your fixed potential is defined by your power supply, which doesn't jump and drop. Capacitors do, but power supplies don't. Okay, so this is a variation of what we sometimes refer to as the loop law, or if you will, Kirchhoff's voltage law. Basically means you take any closed loop and you add up all the voltages. And by definition, in this case, it's all the voltage rises. A drop is a negative rise. They add up to zero, if you will. But ultimately, it's about what's going on when you start and end at the same place. So, we're going to say a few things about this, and we maybe do some calculations and think about how all of this is related now. Well, if we wanted to know something about how much current, for instance, is driven across a circuit, and how much work is required to drive that current across a circuit, or that electric charge, what rate at which you drive that charge across a circuit, we might note that the potential across R1 is related to how much current flows through R1 times the magnitude of the resistive properties of that particular element. It's almost law. We've seen this one, we've talked about it a couple different ways. But ultimately, what will determine that voltage drop, or that electric potential difference, will be in fact related to the amount of current that flows proportionally and the amount of the resistance. Same for V2. And by the way, I'm going to call this I1 and I2. I don't want to just call this I. I want to be very specific that when I say the potential across here, I'm talking about the current physically flowing. So if I can change those here, I'm going to call this current I1. I'm going to call this current I2. So I've got a current I, which is what comes out of the power supply. And I've got a defined current through the first resistor and a defined current through the second resistor. But if I've got a certain amount of charge flowing out, I'm going to have a certain amount of charge flowing in, because there's no net charge associated with this conductive pathway. It's just going to flow continuously. So, in both cases, the requirement for the electric potential is how much current flows across. Or if you will, the amount of current that flows across it is dependent on the potential difference. Now the nice thing is, since they're in series, the current that flows out of one or through one will be the same current as flows through the second one. And by the way, this is probably a better way of thinking about what a series connection is. If you're ever concerned how things are lined up, if all the current, the identity of the current, not just magnitude, the identity of the current that flows through one element corresponds to the same current that's flowing through the second one, it's in series. Yes?
So the I at the beginning and the I at the end are the same?
They have to be the same, yes.
So did they increase to make the V drop?
Yeah.
Yeah.
But let's think about this for a second. So first of all, this implies that whatever the current flowing out of the power supply is, it will be equal to whatever the current is through the first resistor, and that should be equal to whatever the current is through the second resistor. Don't know what it is, I just know that it is. Now what else do I know? This is where the Zen of electric circuits essentially comes in. This is pretty much the hard part, is how are these things related? Well, I can approach it this way. When I have a one loop, usually the easiest way to start is to say, for this loop, power supply, which will drive the electric charge around the loop in the first place. Well, that's 9 volts. That will be equal to the voltage that the potential difference across that first resistor, plus the potential difference across the second resistor. And we can re-describe or describe these quantities in terms of the corresponding current and resistance. this quantity, current times resistor 1 plus current times resistor 2, must add up to 9 volts, because basically if you walk your way around any loop, you have to start and end up at the same place, otherwise you're missing something in the circuit. Because no voltage drop happens along the wire itself. At least negligible drop. Well, the nice thing is, in this case, we can think about this two ways. The nice thing about this is, if I just solve for I, there's always a different way to solve. You can approach these problems in multiple ways. If I just solve for the current, this current is going to be equal to 9 volts divided by, if I factor out the I, the combination of these resistors when they're in series, just adding them together. And to this end then, let's go ahead and give these some values just so we have something to work from. So let's give R1 a value of 100 and maybe R2 a value of, well, let's make it 100 now, so we'll keep the numbers relatively simple. Of course, I should have made that 10 volts, but what the hell. So in other words, the amount of current that is drawn out of the battery, which will correspond to the amount of current that crosses the first resistor, which is the same as the current that flows to the second resistor, which will be the same as the current that flows back into the power supply, will be related to the voltage rise due to the power supply divided by the combined series resistance. So in this case, 9 volts divided by 200. Again, resistance can be described in multiple ways. One of them is volts per ampere. I'm going to write it that way. Yes, it's an ohm. But an ohm is a volt per ampere. So when you look at it, you can see right away, oh, the volts cancel out. I've got an amp in the denominator of the denominator. It's a numerator quantity. So how much current is flowing through this thing? Well, it's going to be
45 milliamps or something like that.
45 milliamps.
Unless I don't know. Let's just do the math here. Yeah, 45 milliamps.
0.845 amps. For now, I'll just keep it SI units. Is that reasonable? So that's how much charge is physically flowing around this thing in any second. So if I wanted to, I could say, okay, well maybe we'll just sort of put this number in here. So I know now that I've got 0.45045 amperes of current that are flowing through this thing. If that's flowing here, that's flowing there, that's flowing there, and that's flowing back into the power supply. Okay, so another thing that we can say about this is that the current is continuous. You may have voltage drops as you go from high back to 0 or high back to low. Current is continuous around this path. It doesn't start and stop, it doesn't get higher and lower, it can't, because if it were any different here or here, then when you calculated the voltages, they wouldn't come out the same as this. So they have to be the same. If for no other reason, then this won't add up properly. And there's no place to bank it, if you will. One electron flows in, another one flows out. Popping marbles through a garden hose, if you will.
So if the resistance is different, does it change the current at all?
Oh, you betcha it does.
Right.
The only thing we can say with certainty is that the voltage as you go around is constant.
Okay.
And the current will self-regulate so that that is the case.
Right.
So these are dynamic systems. They adjust in equilibrium in order for this to be the case. Because the only thing we know for certain is that you start and end at the same voltage. There's no way around it. So, but to this end, without even changing resistors, I'm going to add something to this, and this will add to our analysis. I'm going to take another resistor I'm gonna add a new connection. And that connection, I'm gonna start right here in between the two resistors. And I'm gonna draw, and I'm gonna connect it across like this. And this is still the case. Right, R2 is R3 now. Make this a little bit smaller. There's R2, excuse me. And here's my current I2 flowing across this resistor. Now, we just make R3 the same as R1 and R2 to make life easy. So we've got another 100 ohms. But here's what happens here. If I don't alter this path, but I add another path, then I maintain the amount of capacity, electric charge can flow across this segment. But I add capacity between the points on either end because I have a second pathway for charge to flow. So without knowing any more about this, what I can say is that there's going to be a voltage drop across this second connection. It's going to be I here, it's going to be over there. It's going to be the same here as it is here, which means whatever the voltage is as it comes out of the first resistor, it's going to be the same as it goes into R2 or R3. And when it comes out, because it's connected at this end, it's going to have the same final voltage as it does over here and at the other connection of the negative connection of the power supply. It has to, because the only thing they're connected to is a wire. Nothing else to alter the charge flow. This is profound. It's profound because it changes the entire equilibrium of the movement of electric charge. Between these 2 points here, you increase the capacity of charge to flow. By increasing that capacity, let's say hypothetically, this charge didn't stay, this current stayed the same. It won't stay the same, but just say hypothetically. The current between across R2 stays constant, but now I add a current, just account for a current that flows through R3. Think about the consequences. If I have a current now that's going to flow through R3, now I've got a greater combination of current between these two together, which would require that I1 have to increase. Because this current has to account for all the current that gets split at this junction. There's no way around it. Oh, I'm losing my pen. If it doesn't have any place to go, other than into this connection, this current has to be larger than these two. If it's larger than these two, and it's larger than it was before, because now you've got I2 plus I3, then I times R is going to be larger. And so this voltage is going to go up, just by virtue of having another path for the charge to flow past it. There's no way around it. So adding that second connection literally changes the distribution of the balance of voltage by virtue of having more capacity for charge to flow through from one end to the other. So, so now we got an extra thing to consider. First of all, I've got 2 loops. I've got one loop here now, and I've got one loop here. Well, without doing anything else, let's think about this for a second. If I start here and I go around the second loop, now I already sort of tried to justify that the voltages have to be the same across. Let's think about this. If I start here and go clockwise, going from negative to positive, my voltage is going to rise. It's not really a power supply in this case. It's a voltage, but because of the direction I'm going from negative to positive, so I'm going up an electric potential hill. As I go around, there's a voltage drop. But when I get back here, I'm at the same point I am here, so I have to have the same voltage across both of them. Again, the idea of that loop rule should be self-evident. The engineers just say, it's Kirchhoff's loop law, voltage law, you just use it. Sure you do, but this is why. So, everything changes. Now we gotta figure out something new. Now we say,
Well, I'm sorry, I don't mean to interrupt, but it seems to me that the electrons are going to want to go to the path of least resistance, and because of that relationship of the ratio of the resistance to that current, then the voltages they're gonna equal out. Is that,
sure, absolutely, it's another way of thinking about it.
that's.
The balance of current will basically self-adjust, because if they have whatever the resistors are, there will be a path of least resistance, which means for a certain amount of current flowing into the junction, it's gonna spread itself out proportionately or
Right.
inversely proportional to the resistances, because it will tend to follow the path of least resistance. Doesn't mean it's only gonna go one and not the other, but it just means the resistor with the lowest drag, if you will just accumulate and allow more charge to flow through than the other end. It's like having two holes and running water through a hose. More water's gonna go through the larger hole than the smaller hole. But the same amount of water flowing in is gonna flow out in combination between the two. Now, if they're the same, then that also says something too, right? If this resistor is the same as this resistor, then whatever current flowing in, you're going to still have the same current I2 as you have I3. Because they have the same amount of resistance. The path of least resistance, there isn't one. They're both the same. If one were slightly smaller, that would change the balance. But as long as it isn't, then the current will just split. Either way, the amount of current flowing between these two independently will be less than what's flowing in. You've got some bulk flowing in, it has to be separated and split apart, which means these voltages will in fact be lower than they were before as the voltage here rises. More charge, more current, higher V1, which means the drop across R2 or corresponding drop across R3 will have to be lower, because top to bottom is still only 9 volts. Everything balances itself out this way. So increasing charge in one raises its voltage, which drops a voltage corresponding to everything else farther down the food chain, if you will, or farther down the path. But the balance has to come out to 9 volts, because the one thing you can say with certainty, the terra firma in this particular process, is that the step from one end of the power supply to the other is fixed. And that will force the balance in everything else. It's a forced equilibrium. No doubt about it. So nothing is independent of everything else. So you have to reanalyze everything, because that balance means that nothing can be constant now, unless it's completely accidental with the numbers. So let's look at it. So this would have been the current I equals I1 equals I2 for the simple loop circuit. But as we add the separate section, now we have more things to consider. At some point, we absolutely make shortcuts and look for simple ways to make things simpler, but you don't have to in order to understand these things. So now we'll ask the same question. With the second connection, what is I still? What's the current that's flowing out of the power supply? What the hell is this? That's what we calculated before. It happened to be equal to the same I1, I2. It's not now. What is it? So we'll play the same game. We've got two things going on. Two ways to process this. First of all, for loop 1, now I have to give some numbers to this. There's loop 1, and there's loop 2. For the first loop, we play the same game we played before. If you start here and go all the way around. Yes.
Does loop 1 include loop, or the V2
No.
part? Okay.
It can. Doesn't have to, though. This is where the Zen comes in, if you will. Okay. So let's look at, I know, and I mean this absolutely seriously. So for the first loop, okay, I'm gonna draw it this way because now this is another way of drawing that power supply. There's your V naught. So my first loop is R1 and R2. Okay? And this is what I know. I know that V naught, which is the voltage across R1, I'm just gonna go ahead and write it as I1 R1, plus the voltage across R2, which is I2 R2. Now they're not the same, damn it. That quantity will equal 9 volts. Well, what else do I know? I've got at least one more loop to consider. So let's look at loop 2. And for this loop, I'm going to use R2 and R3. I'm going to start here, and I'm going to walk my way around. So, what do I know? Well, I know that I2 better be equal to I2R2 will be equal to I3R3. They have to be equal. The voltage rise equals a voltage drop in magnitude.